Hello everyone, this is Dr Guessoum Hanni, Assistant Professor in the Department of Automatic Control, USTHB's Faculty of Electrical Engineering. Today we are diving into discrete event systems, a powerful way to model systems where change happen in sharp, event-driven jump, not smooth flows. Why it matters. From optimizing video games, servers, and streaming Amazon warehouse, discrete event systems help us design smarter, faster systems. It's the hidden logic behind efficiency in tech, manufacturing, and beyond. Now that we have set the stage, let's define what we mean by discrete event system. A discrete event system is a dynamic system where the state evolves over time, but unlike in continuous system, such as those describing fluid flow or temperature change. The state changes only at discrete moments and only in response to a specific event. These events are instantaneous and often asynchronous. That means they don't occur in regular intervals, but rather are triggered by something happening in the system. For example, in a manufacturing plant, an event might be a machine breaking down or a task being completed. Key characteristics of discrete event system include event-driven behavior. The system reacts only when something specific happened. Discrete states, it shifts from one distinct states to another. There is no gradual transition, often non-deterministic. Some systems don't follow a predictable path, so we may need probabilistic model to understand them. A classic example is a traffic light system. The light changes state, say from red to green, only when timer expires or when a car is detected is a clear illustration of how discrete event drive state change. Understanding this basic concept is fundamental because it's the foundation upon which all our modeling, analysis, and control strategy for discrete event system will be built. To work effectively with discrete event systems, we need to understand three core concepts: event, states, and transition. Events are instantaneous actions like part finishing, a message arriving, or a machine breaking down. States describe the system at specific time, like a machine being idle or a buffer being full. Transition are how the system moves from one state to another, triggered by events. Once we understand the basics, we need tools to model discrete event system precisely. We got many key formalism like Petri nets, which is great for visualizing concurrency and resource sharing. Finite state automata, which is useful for modeling sequential decision logic. We also use other tools like GraphSet and Max Plus Algebra, along with simulation software such as Arena or AnyLogic for more complex systems. These tools help us simulate, analyze, and improve real-world system efficiency. After modeling, the next step is analyzing performance and designing control. Performance analysis looks at efficiency, like throughput or delays using simulation and queuing theory. Control design ensures the system behaves as desired, avoiding deadlocks or optimizing schedules, often using supervisory control theory. These methods help us make systems not only functional but also optimized and safe. Let's now look at how discrete event systems are applied in the real world. This is where theory meets practice. Discrete event systems are used in industries where timing, sequencing, and resource coordination are crucial. In manufacturing, discrete event systems models help optimize automated assembly lines and reduce production delays. For instance, improving the cycle time in semiconductor fabrication by even 10% can save millions. In logistics, they are used in managed flows in automated warehouse or port operation, like making sure parcel move efficiency throughout a conveyor system. In computing network, discrete event systems help simulate and manage network traffic, ensuring protocols like TCP, IP prevent data loss. And in traffic management, these models guide the design of smart traffic lights or airports ground operation to reduce delays. In all these cases, discrete event systems allow engineers to simulate, predict, and optimize system behavior before any real-world implementation. So, as future engineer and system designer, understanding these applications will give you a solid edge in tackling complex dynamic environment. While discrete event systems offer powerful tools, it also comes with significant challenges, especially as systems grow more complex. The state explosion problem is a major issue. As systems become larger, the number of possible states increase exponentially, making them harder to analyze. Uncertainty and variability in real environment require us to model randomness and make systems more robust. Hybrid systems, which combine both discrete and continuous behaviors, are increasingly common, especially in areas like robotics and autonomous systems. We are also seeing exciting emerging applications such as cyber physical systems, smart grids, and artificial intelligence driving control. Finally, machine learning is starting to play a role, helping discrete event systems adapt in real time and perform predictive maintenance. These challenges are not limitations, they are opportunities for innovations, and there's where your generation of engineers and researchers can make a real impact. As we come to the end of this introduction to discrete event systems, it's important to reflect on the broader significance of what we have explored. Discrete event systems are not just academic concepts. They are essential tools for understanding, modeling, and improving complex real-world systems. Systems that are all around us, in factories, airports, data centers, hospitals, transportation networks, and even in the device we use every day. What makes discrete event systems so powerful is that they give us a structured way to think about change, specifically changes that happen due events. A machine starting, a message arriving, a train departing, unlike continuous systems where change happens smoothly over time. Discrete event systems focuses on what happened when it happens and what that caused. This is exactly the kind of reasoning we need in an environment where timing, coordination, and decision making are critical. Thought modeling and analysis, discrete event systems allows engineers to predict system behavior, identify bottlenecks and failures before they occur, optimize performance, and ensure reliability and safety under complex constraints. As we have seen, the impact of discrete event system is not limited to one field. Whether you are working in manufacturing, logistics, telecommunication, healthcare, or artificial intelligence, the principles of discrete event system are universally applicable. But while the tools and techniques are powerful, the true value of discrete event system lies in how they are applied with growing system complexity. The challenges we face, like the state explosion problem or dealing with uncertainty, require creativity, abstraction, and often the integration of new technologies, such as machine learning and real-time data analytics. This is where your role as next generation of engineers, system designer, and researchers become crucial. By mastering discrete event systems, you equip yourself with the skills to design smarter systems, to optimize resources, and to contribute to innovation across domains. You gain the ability to move from reactive thinking to proactive predictive control, and that's a powerful shift. In short, discrete event systems give you the language, the logic, and the tools to make complex systems not only work, but work better. So, as you continue your studies, I encourage you to look at the system around you and ask, what event drive them? What state do they pass through? And how could they be improved? Because that's the mindset of someone who doesn't just observe the world, but improve it. Thank you.